Welcome, everyone. We're just going to give it a few minutes for everyone to get settled on the Zoom call, and then we'll get started. Thank you all for joining. All right. Hello, everyone. Thank you so much for joining us today for our CMAS Center webinar series with Dr. Manish Soni. We're really excited to have all of you here to join this talk. My name is Sedona Ryan, and I'm the Research Project Coordinator at University of North Carolina at Chapel Hill's Institute for the Environment, which hosts the CMAS Center. For today's webinar, a bit of logistics, you can feel free to post questions using the Q&A feature at any point throughout the presentation. And if there are any questions about logistics or Zoom and those kind of things, I'll answer those as they come up as I'm able to. But otherwise, we'll save all of those questions that come in from the Q&A for a designated Q&A portion at the end of the talk. And you'll also be able to raise your hand at that point where we can unmute you. If you have maybe a longer, more discussion type of question, you'll be able to do so at that point at the end of the webinar. So with that, I'm going to introduce the Director of CMAS Center, Dr. Saurabh Arunachalam, who will be introducing Manish as well as sharing some upcoming events and opportunities through the CMAS Center before we begin. So thank you, everyone.
Thank you, Sarona. Greetings, everybody. I'm pleased to welcome you all back to our webinar series. We took a small pause on the webinar series and glad to resume it now with Dr. Manish Soni going to present shortly. Before we turn it over to Manish, I just have a few announcements I want to go over to inform the community of what is coming. The first one is there are 2 rounds of trainings coming up this year. As most of you probably know, we have trainings on SMOKE and the CMAQ models in spring and again in fall. The spring dates and fall dates are posted on the calendars, and we do have some slots open. For people who are interested, please join us and register soon. And the next slide, please. And we are pleased to announce our 25th annual CMAS conference later this year. It's fixed for the week of October 19th. It'll be in Chapel Hill. The call for abstracts announcement will be coming pretty soon. Please stay tuned for this announcement. And then some of us who have been trying to port these models in the cloud may know that CMAS Center has been organizing, hosting help sessions. These are monthly help sessions hosted on Zoom, hosted by the CMAS Center staff. And the audience is for people who are trying to run the model in the cloud, similar to what Manish will be presenting in a few minutes. And the goal is to provide one-on-one support to members of the CMAS community. It's free. We cover multiple topics from using CMAQ or HPC performance on AWS or Azure, benchmarking model based upon our own experience. And we'd, of course, like to learn from the community in terms of what they are trying to do and how we can perhaps help you based upon our own lessons learned the past several years. It's the first Thursday of every month from 3 to 4 Eastern. And here are the dates at the bottom of the slide. April 2nd is the next one. So please do take advantage of learning from the CMAS Center experts to see how they've been able to run the models in the cloud and perhaps helping you for your own projects. Next slide, please. The last announcement I have is to announce the next webinar in the series. So today Manish will be presenting, and after this we have the next one already planned for May. So on May 13th, you will hear from one other CMAS staff member with Liz Adams that most of you may know on exploring how to run CMAQ AMET, the atmospheric model evaluation tool, on the cloud. So working with the EPA, there's a version of AMET that runs on the web. So we have ported this on an AWS instance. You will learn how the install works for taking AMET to the web, and then we'll have a short demo of the various features of the new AMET. So this is on May 14th. The dates are fixed at 1 p.m. Eastern, same time as today. And there's some initial documentation already available on our Read the Docs cluster. So stay tuned for this. On top of that, I do welcome anyone else in CMAS community to join us and giving your own webinar on topics of interest to the community. If anyone is interested, please let us know and we'll schedule you after May 14th. With that, I'm pleased to introduce Dr. Manish Soni, who's going to give this presentation today. Manish is a postdoc with our center here at UNC for the past 4 years or so. Before that, he has two postgraduate degrees, one in Master of Computer Applications sometime back, and then he has a PhD in physics after his master's in computer applications. Manish has been an integral part of our team doing multiple CMAQ modeling application and evaluation analysis. But here he'll be presenting a specific aspect of what he's been doing with other co-authors here in our experience on learning running CMAQ on the AWS for long-term simulations. With that, I'll turn it over to Manish.
Thank you, sir. Good afternoon, everyone. I'm Manish Soni from UNC Institute for the Environment. Today, I will be sharing lessons learned from running long-term simulations using AWS Parallel Cluster, focusing on CMAQ as a case study. So the outline of the presentation is I will start with the motivation and problem. Then I will introduce CMAQ modeling system and AWS Parallel Cluster. Then move into benchmarking, performance, and cost. And finally, lesson learned and recommendations from us. So let's start with why this matters. So our motivation is long-term CMAQ simulations require significant high-performance computing resources. Air quality matrices for regulatory applications or quantifying health impacts and climate interactions need annual or even multi-annual simulations. So cloud computing enables scalable HPC environment, and Amazon Web Service Parallel Clusters simplifies the cluster deployment. So why we need this? Because these simulations are computationally intensive and they require high performance computing resources. So before going to anything, I would like to define what is AWS Parallel Cluster. So AWS Parallel Cluster is an Amazon Web Service Parallel Cluster. It is an open source tools that automatically creates and manages HPC clusters in the clouds. It handles provisioning of the compute nodes. Job scheduling is through the Slurm, and you can scale resources based upon your workload. So from a user perspective, it behaves very similar to a traditional HPC cluster, but with the flexibility of cloud resources. In this study, we are using CMAQ as an example application, but the workflow and the findings are applicable to other HPC applications or models as well. So it is not only limited to CMAQ. So problem statement is traditional HPC clusters, they have limited availability and fixed capacity. Cloud computing provides on-demand scalable resources. However, we should always look for the cost and performance trade-offs because we are paying for what we are using. So that's why we have to look for the cost as well as the performance. So our goal here is to identify cost efficient Amazon Web Service configuration for CMAQ production runs and to perform a long-term simulation on AWS Parallel Cluster and provide guidance for the CMAQ community. So we are trying to identify configurations that are both efficient and cost-effective, and so that we can provide guidance to the users. This is a CMAQ typical modeling framework, and CMAQ is CMAQ simulates ozone, PM2.5, NO2, etc. for different air quality applications. It is widely used in regulatory and research applications. It requires large-scale, high-performance computing resources. The typical production run requires annual simulation. So most broadly, it represents computationally intensive resources. Uh, that's why we are trying to use cloud for this. So for this study, we have used two domains, 12US1, which is the final resolution domain, and it is more computationally expensive. The grid size is 499 by 259, and 36US3, a coarser resolution. This should run faster, and it has less grid cells also. So these are the two domains that are used for benchmarking computational cost, and we have tried different compute, and they also require different compute and storage requirements. So we have used different computer config and compute node configuration, so to see what's the best one. So before going to parallel cluster, it is very much essential to learn about single virtual machine and the parallel cluster. So single virtual machine is just like a server, a single node server, which has which have single fixed CPUs, memory, and storage, where all the tasks run on one node. It is very easy to set up, but has very limited scalability and performance. And when we are talking about parallel cluster, uh, it is highly scalable. They are the group of multiple interconnected machines that work together to execute tasks simultaneously. It provides higher performance, scalability, and is mostly suitable for large scale simulation or high performance computing workloads. It has a more complex setup, but it can handle parallel jobs also. So, for example, single VM is running a single CMAQ simulation on one EC2 instance, and parallel cluster is running CMAQ across multiple nodes using MPI with faster interconnect like AWS Elastic Fabric adapter, which is a network interface for faster intercommunication within nodes. So you should have a very low latency in between the node. So for running AWS parallel cluster, you need to have some prerequisites. So the prerequisites are you should have a AWS account and with billing enabled. So you should have a credit card enabled there, and you should have the access to AWS management console. The user must have the permissions to create and manage AWS resources like EC2, virtual private client, Lustre storage, S3 buckets, and he should also have the privilege to do the auto scaling. So for this, you should have a command line interface installed and configured to your local machine to interact with the AWS services. Uh, so the since I told you that it is an open source tool, so it has the AWS parallel cluster is developed in Python. So so you should have a Python environment 3.8 or later to install and run parallel cluster tools. You should also have a key pair, just like you are connecting through a server. You need you are doing SSH and you need a key pair. So you should also have a key pair for a secure SSH session to to log into the cluster head node or the login node. Also, you need to have a virtual private client networking setup that can connect through which you can connect. So the HPC instances are available are HPC 7G, HPC 6A, and HPC 8A. They are mostly developed for high performance parallel workload. You should be able to add Lustre storage, S3 bucket, or shared storage as per your need. And after running your simulation, you can always archive your data to S3 bucket for less cost. So this is a typical AWS parallel cluster. So what happens is a user or a client submit a request to a API application program interface gateway. Then AWS Lambda. AWS Lambda process that request and triggers the cluster operations. And it goes through the login node, and login node manages the cluster and the job scheduling. So jobs are placed in the queue, and once Slum, the thing is the Slum dynamically provision the compute nodes and deregistered them once the job is complete. So it also ensures that the compute costs are only incurring cost during the job execution. So AWS also support Lustre and Elastic Fabric adapter for interconnection between the nodes, and Lustre for higher throughput and higher input output operation. So you can drive faster. And once the simulations are completed or your job is completed, you can always move them to another local drive, or you can move it to a S3 bucket. So first, let's look at the storage and the networking. You have a elastic block storage, which have maximum input-output operations per second and a higher throughput. That is how much work load it can handle. And it also this EBS also allows user to provision performance independent of the storage capacity. It has high performance and low latency disk. So for this, we have Lustre that can handle, that can process massive data sets at up to hundreds of gigabytes per second of throughput. And it can handle millions of input-output operations per second. And it has sub-millisecond latencies. And the, the good thing with Lustre is you can always use a S3 bucket along with Lustre to load your input data when it is first used from S3 bucket. So you can always point in the configuration file that you have input data at this S3 bucket, and it should load it from there. And S3 bucket is a simple storage service which is used on the parallel cluster. You can archive data at the lowest cost, and you can run cloud native applications by loading the data from S3 bucket to Lustre drive. So the networking options which we have used is EFA, and it has high throughput. So for deploying the parallel cluster, we choose two regions. So we chose US East 1 and US East 2. US East 1 located in Ohio and US East 2 located in Northern Virginia. We have used two kind of setup: ARM64, that is advanced RISC machine cluster using Graviton 3 processors, and x86-64 cluster using AMD EPYC processors. So AMD EPYC processors are similar to what we have at UNC Sycamore. So UNC Sycamore cluster, they also use AMD EPYC processors. We have built separate build environment for both the architecture for benchmarking runs. Surprisingly, ARM64 doesn't support Intel compilers, so we have only installed GCC build environment on ARM64. So compiler installed on x86-64 are Intel and GCC, and on ARM it is GCC. So earlier the Intel compilers were were costlier, and so now the Intel compilers, they are coming from free, and you can install the latest Intel compiler. They have their own MPI, so you can use the same MPI, and the setup is also easy using a simplified SH script, and you can also load it as a module. So it is much more easier now. So you can use Intel latest compiler for free. The operating system which we have used is Ubuntu, and the parallel cluster version is 3.12. So this is the typical AWS parallel cluster architecture for CMAQ, which we have used is we have a command line interface, and we have a login node, and we submit the job through a Slum, and Slum provision the jobs on the compute nodes, and then once the job is complete, you have the data at your shared storage, and then you can move it to S3 bucket. So we should always ask, we are always asking the question, why HPC EC2 instance are required for CMAQ? Because CMAQ required highly parallel HPC compute resources, So that's why we use HPC instances. And these HPC instances are built on AWS Nitro system, and they have a very low latency internode communication. So communication is very fast, and the response time is minimal. And it has up to 200 Gbps network bandwidth for tightly coupled workload. So this enables us for highly scalable CMAX simulation. So if we talk about the login node cost and compute node cost and the architecture is, so the login node for x86-64 is C6A X large, which has 4 cores and 8 GB RAM, and you can procure this as $0.5 per hour. And the compute nodes for these are HPC6A 48X large, which has 96 cores and very high RAM, 384 GB RAM, and you can procure this at $2.88 per hour. And these nodes are available in US East 2 regions compute nodes. And for ARM64, we have used C7G.large, which is 2 cores, 4 GB RAM, and you can use them at $0.07 per hour, almost half the price of what you have for Intel cluster or x86-64 cluster. So for compute node, for ARM64, we have used HPT7G 16X large with 64 cores and 128 GB RAM, and you can procure this as $1.68 per hour. And this is located in US East 1 region. So for benchmark methodology, we have a test conducted using the 12 US1 domain, and the performance metric which we have chosen is average CPU time seconds per day. So how much time it takes for a 1 day simulation. We have evaluated different processor counts, and we have used both shared storage as well as cluster storage. The CMAQ version which we have used is 5.4 plus, and the mechanism is carbon bond 6, aerosol module 7. The compiler which we have used is Intel and GCC. So this is typical AWS parallel cluster workload, how you are starting and how to run the simulation. So for that, you have to activate the Python command line interface on the local machine or on the server from which you are connecting. Like we have Longleaf and Sycamore, so we can log into Longleaf and Sycamore, and we can install our command line interface there and parallel cluster version also there, and we set up the build environment there, and then we activate it. So this is the first step. The second step is we configure the cluster using the command line interface. So once you have the AWS account billing enabled and you can access using the command line interface, and you have the VPC and the subnet ID with you, you can do all the things with command line interface and using a simple YML file. YML is yet another markup language file which contains the cluster configuration. That means what is the login node you want to use, what is the VPC client, how much shared storage you want to use, how much cluster storage you want to use, or whether you want to load your data from S3 bucket. So all those information is in the YML file. So this particular example, what you are seeing is for the ARM64, which has HPC7G.16x large. So it has the YML file. This is the YML file. So you should configure this YML file, how you want to configure, whether you want to run on shared storage only or the cluster storage. So you can modify this file. So once you modify this file, you can create the parallel cluster. For that is the fourth step. Your P cluster, create cluster, and then you have to specify the cluster configuration file, which is HPC7G. Then you have to specify the name of the cluster. For this example application, the name of the cluster is CMAQ, and you also have to specify the region, that is US East 1. Once you invoke this command, you can always check the cluster status because it will say whether it is working on or it is done. So once the process is complete, you will see the status okay. So once the status is okay, then you can log into this cluster by using the sixth step, which is cluster SSH, just like you do log into your remote server, you can do like the same way. So once everything is set up, you can always log into this, AWS parallel cluster, just like the way, uh, you log into your local, just like the way you log into your HPC server, uh, traditional HPC server. So you should have a PAM file or a EC2 key pair to log into this server and specify the cluster name. Then once it is there, you configure your run script, you have your input data, and once the run script is configured, you can run the CMAQ simulation. So once the run script is submitted, the login node, the Slum provision the compute nodes. And once the compute nodes are provisioned, the simulation is run. And so you are paying for only the amount of time when your compute nodes are active. Okay, so you can save cost also. That your compute nodes are only incurring the cost when during the job execution. And once the job is complete, uh, you can use the luster for output. So once you are finished up with the simulation, you can always delete the cluster after taking the uh, after archiving the output through S3 bucket or your local drive. So we have some experience working on this. So we have a complete setup, step-by-step method how to install and create single virtual machine and parallel cluster, and it is available in the below links. We also have pre-configured YML file and run script which you can use for running CMAQ version 5.4 as well as CMAQ version 5.3. So these are the pre-configured YML file which you can use, and run script also is there that how can you run using the AWS parallel cluster. So at CMAS Center, we continuously encourage people and to use how to encourage users that they can docker the data without incurring any cost, and we always provide facilities to the users. So we have a CMAS data warehouse, and it is on AWS. It is a CMAS center repository where we disseminate metrology, emissions, and air quality model input and output for community multi-scale air quality model application. This repository is available as a part of AWS Open Data program. So there is no egress fee that is charged to user or the host for downloading the data. This public S3 buckets are hosted by CMAS Center on behalf of US EPA Office of Research and Development and US EPA Office of Air and Radiation. So metadata for the data warehouse is also available at CMAS Data Warehouse and at this link. These are the data available at CMS Data Warehouse. This is not limited. We have more data available at CMS Data Warehouse now. For this study, we have used CMAQ benchmark data for 12 US1, and for 36 US3, we have used 2023 36 US3 data, and which is available from Genodo Drive, and which is also highlighted in red. So you can, if you click on this link, you can have this data and you can reproduce the results. So for benchmarking results, these are for the 12 US1. So we have HPC 6A, which represents x86-64, and HPC 7G as ARM64. So whenever you are seeing hatching lines, that means we are using HPC7G or ARM64. So the first blue bar, just Just a second. Just sorry. So the first blue bar is for the Intel compiler, and 2700 is the time for one day simulation. And this is on Intel. On GCC, the seconds are 2600 seconds at 128 nprocs or 128 number of processors. So on x86-64, the GCC performance is better than Intel, though when we are seeing HPC7G on ARM64, the performance is much better than x86-64 and also at a lower price. So we are seeing that that improving the nprocs from 128 to 198 improves runtime for all the configuration. HPC7G plus cluster gives the best performance among all of them, and GCC on HPC7A is faster against Intel, though HPC7G performs better for both 128 and 192 cores. If we go by this, the annual simulation time it takes is around 7 to 11 days for 12 US1, depending on the processor counts and cluster configuration. The table below here is the table for HPC 6A and 7G and the cost. And the cost here is includes the login node and the compute node cost. So suppose it has two nodes, so the cost is login node plus 2 times of the compute nodes. If it has 3 nodes, then login nodes plus 3 times of the compute nodes. So when we are going from so HPC6A, it takes $5.91 per hour, and with the ARM64, the cost is $3.44 only per hour. And when we take 3 nodes for HPC7G, the cost is 5.12. And so here we are seeing that the performance is better for ARM64, and we are also seeing that the 12 US1 benchmark demonstrate good performance scaling, and we are increasing processor counts, improves the runtime, and HPC7G plus Lustre drive provides the best performance among the tested ARM-based setup. So if we look at the key findings from this is that GCC outperformed Intel compiler on x86-64 by 4 to 10% for 12 US1, and GCC on ARM64 was around 24% faster than GCC on x86-64 for 12 US1. HPC7G instances offered strong cost performance. ARM processor reduced CMAQ compute cost by 50% compared with x86-64 configuration. So on the basis of this, ARM64 was selected for the production run for 36 US3, which was our output goal that we want to run for 36 US3. And Lustre drive also improved the parallel input-output performance. So this is these are the results for 12 US1. So once we have selected that we will be using ARM64 based upon the cost and the performance from the earlier plot, so we tried to mimic different processor counts on ARM64 also, like 64, 128, and 192, with different domain decomposition also, that to check whether domain decomposition can also help in speeding up the process or runtime. So what we saw is when we have 64 processors, we have around 630 seconds for a single day, because 36 US3 is a core serve resolution, so it is much faster. For 128 cores with domain decomposition of 4 by 32, it the one day simulation was completed in around 400 seconds, and for 128 nprocs, it was completed in 363 seconds with a different decomposition 8 into 16. So 4 by 32 takes 411 seconds, and 8 by 16, 363 seconds. So there is a performance, you can save around 40 seconds per day by just changing the domain decomposition. And when we are going from 128 cores to 192 cores, the runtime is further reduced to 287 seconds. We haven't done from 192 to 256 because we have some experience where we saw diminishing return when we are going from 64 to 128, 128 to 192. From 192 to 256, we have diminishing returns. So that's why we haven't gone up from 192 to 256. That's the same reason we haven't used the same for 12 US1 also. So by this we can say that 128 nprocs already provide a strong performance, and best performance is achieved with 192 nprocs, and from which we can reduce the runtime from 3 to 1 day. So when we use 64, the annual simulation is completed in 3 days, and when we use 192 cores, we can complete the simulation in 1 day. So 36 US3 also covers a larger area, but due to the course resolutions, runs are much faster and cheaper than 12 US1. So the annual simulation time ranges from 1 to 3 days, depending upon the processor count and the cluster configuration. So if we go from 2 nodes to 3 nodes, the price is 3.44 for 2 nodes, and the price is $5.12 per hour for 3 nodes. So when we increase the configuration from 2 nodes to 3 nodes, the compute cost is increased by $1.68 per hour, around 49%. And the runtime is only improved by 26%. So based upon this, we only chose 2 compute nodes to save more cost because we are getting equivalent performance. So that's why we chose 2 nodes over 3 nodes. So for running the simulation, you should always look for how much storage it will occupy for the annual runs. So once we run for a single day, we did a 3-day test, and we took the average of that, and we found that it takes around 7 GB for a single day output, which single day input and output. So this storage includes your inputs from metrology, emissions, initial condition, boundary condition, and also output 2D and 3D. So annual storage, for storing the annual storage, you will require around 3 TB of storage. And when we are talking about 12 US1, it takes around 90 GB per day it includes input and output. So around 36 TB storage is required on Lustre or shared. So we have the compute cost. We should also look at the storage cost. So for 36 US3, we only provision around 2 TB, and for 12 US1, we only provision around 18 TB. So with the new Lustre configurations, you can save money, half of the money, by using data compression. So in the earlier slide, I told you that we require around 36 TB. So 36 TB, then if you use the data compression method, then you only have to pay for 18 TB. And this is a new method, and so you can always save half of the disk space. So once you have 18 TB available, you will only pay for the 18 TB. And the cost for this is around 0.145 per GB per month. So the cost which you are seeing here is when we are provisioning the Lustre storage for 1 month. Because we know that the simulation took around 11 days maximum, but we need some time for cluster setup, benchmarking, and simulation runtime, post-processing, and data transfer to Amazon S3 or local bucket. So that's why we have provisioned it for 1 month, and the cost is around $3,000 for the Lustre storage itself. Okay, so This is the cost for 12 US1. Similarly, we use the same configuration, same method. So for 3 TB, we will require only 1.5 TB. But the thing is, from Lustre, when you are provisioning a Lustre storage, you can always choose either 1.2 or chunks of 2.4 TB. So you will be provisioning 2.4 TB for 36 US3, and it will cost around $350 with the same method. So when we look at the total estimated cost per annual run, so for 12 US1, the cost is around, for compute cost is around 800 to 600, depending upon the architecture, processor, domain decomposition, and the compiler use, and $3,000 flat charge for your storage. And for 36 USD, the compute cost is $120 to $220, and the Lustre storage cost is $350. So it also means you are always paying more for the storage rather than the compute cost. And actual Lustre storage time can be typically shorter based on the user needs. So for 12 US1, the annual cost is around $3,800 to around $4,600. And for 36 USD, it will be within $470 to $570. So this is the estimated cost when you are running the annual simulation in one go. Okay, that means you have metrology, emissions, each and everything available for the entire year, and you are running a single simulation from a single simulation, and you are running it for the for 365 days. So the storage strategy is you use Lustre during the active simulation because it provides high performance parallel system. In our study, we have multiple simulations, emission scenarios that shared the same input. So we created a shared drive. So once the simulations were completed, we copied it into shared drive and then post-process, then archive it to S3 bucket for retrieval to our local server. So the recommendation from us is you store the active simulation output in Amazon S3 bucket for faster access, while long-term archive data can be moved to S3 Glacier storage, which can significantly reduce the storage cost. So the S3 cost will be in the next slide. So these are the costs for the S3 bucket on Amazon. So if you use a standard S3 bucket, it will cost you around $0.023 per GB per month. But if you move it to Glacial Deep Archive, it will be stored in 0.00099. So you can store 36 TB data in less than $100 or around $300 using the Glacial Deep Archive for a month. So it is much better. So using Glacier Deep Archive can reduce the storage cost by over 95% compared to S3 bucket for long-term archive data. This you can Glacier Deep Archive you can use when you you really want to access the data, and the access time is up to 12 hours retrievable speed. So this is the typical workflow which we have used on ARM64 for our 36 US3. So we have 6 months simulated from April to September for 3 years, each with 3 emission scenarios. So we have in total around 9 CMAQ runs. So how did we choose the environment, we create the parallel cluster, we copy our inputs from the local, and we run 6 months simulation, and we archive the raw output to S3 bucket. We post-process it before archiving the output, and then we just download the combined and our 2-day post-process output locally for ML evaluation and for post-analysis. We QA and evaluate it, and we review the model performance, and we clean the storage uh, and remove FXX if needed. Otherwise, since we have multiple scenarios, we just repeat the next scenario and continue to other runs. Once we have all the 9 runs completed, we delete the Lustre storage because it will be procuring higher cost, and we move all the data to S3 S3 bucket for downloading it to local or keeping it for later use. So let's look at the lesson learned, how to save the cost. So initially, when we estimated our cost, they were 2x lower than what was the cost which we have incurred, because we have changed the CMAQ version, we have some repeated runs, and initially when we choose the luster, we haven't used any compression. So we were paying for the entire drive and it doesn't had any compression. So we paid for the 3 TB itself instead of paying for 2 TB. So storage costs can be reduced if we are using archive compress and which is cost efficient luster. And earlier the speed was 50 Mbps terabyte. So the cost was higher, okay, and it was the default option. Now the default option is the persistent 128 Mbps TB or the scratch drive, which has higher throughput and which is available at much cheaper price at 50 Mbps TB luster drive. So you can save by this also, because this is available at 0.6 USD. Okay, and this is available at 0.145. So the cost is much cheaper. So the method is you can use a small root and shared volume, keep all the input output data on Lustre, and disable or delete the Lustre drive when not in use to save the cost. So the cost calculator below is shown for persistent Lustre drive with 50 and 125 Mbps TB configuration. So I told you that we have 3 TB for 36 US3. So, so if we use compression, we have around 1500 GB, and for 1500 GB, we have to procure around 2 TB, 2.4 TB hard disk, because you can only procure either 1.2 TB, 1.2 TB, or chunks of 2.4 TB on the luster. So with 50 Mbps, the price is 0.6 per GB. So you will be procuring the cost of around $1,500. And when we use 128 Mbps TB, which is at higher throughput and higher throughput. So even with higher throughput, you are incurring very low cost, almost 4 times cheaper. That is 0.145. So it is around $350 dollars. So you are saving almost 4 times of what you are getting from 50 Mbps TB. So even at a lower speed, it is at a lower speed and you are getting a higher speed at a lower cost. So you can save more. So let's look at the cost and performance advantages of ARM64. So you have a better price to performance ratio for ARM64. ARM64 was 24% faster than x86-64 in CMAQ 12 US1 benchmarking using the GCC compiler. You have a lower compute and login node cost, over 50% saving for login nodes, because ARM64 was procured at 0.07, and for x86-64 the cost was 0.15. So you have the 50% saving in the login nodes and 40% saving for compute nodes. The compute nodes for x86-64 was available at 2.88, and for ARM64 it was available at $1.68 per hour. So you are saying 40% here in the compute nodes itself. So 50% saving in login nodes and 40% saving for compute nodes. You have an improved efficiency for CMAQ because it provides faster simulation with lower overall cloud computing cost, because you are saving too much with ARM64. So our recommended configuration is using HPC 7G instances. It also depends upon your application, what kind of application you are using. I am showing an example of CMAQ, but it is not limited to CMAQ. You can use any kind of application, and you can have your own benchmark, but you can have this recommended configuration that you know how to save the cost for processing as well as storage. The compiler which we are recommending is GCC, storage is Lustre drive, and And another good way is you should delete the luster after your simulation or your application run is completed and move your raw CMAQ outputs to S3 Glacier to S3 Glacier drive. Advantage of AWS parallel cluster is you have a scalable HPC environment. You can have the automated cluster management. You can integrate with AWS storage services like Cluster, S3 bucket, and EBS shared. This is very good, suitable for research workflows. Implications for CMAQ community is you can use cloud HPC enables flexible research infrastructure. ARM processor reduce the simulation cost. You have the optimized storage strategies that can minimize your expense. It can be useful for multiple long-term simulation. So the future work is benchmarking CMAQ DDM with multiple sensitivity variables, and to evaluate additional new compute instances and storage options because AWS releases new compute instances, for example, HPC 8A. As EPA also reviews new versions of CMAQ, so they need to be benchmarked also. Uh, we also want to automate CMAQ workflows in cloud like provisioning compute nodes, pulling input data from S3 bucket, submitting job, post-processing, archive outputs through S3 bucket or the local drive, or removal of resources after job completion. This we want to automate and improve cost optimization strategies, efficient storage options, choosing right-size compute resources, use HPC instances, auto scaling, shut down or idle resources, optimize data transfer using compression, cost allocation tags for different projects where from which you can tag which what project incurred what kind of cost. So you can also do that using the AWS. So these are the references which we have used, and I like to acknowledge US EPA through its Office of Research and Development, which was partially funded and collaborated in the research described here under contract. And we also like to acknowledge Amazon Web Service to support for the CMAS Center data warehouse to its open data program through which the user can download the input data or the benchmark output data at no cost. And I also like to acknowledge US EPA CMAQ development team. I also like to conclude in a manner that it AWS parallel clusters enables the users for scalable HPC in the cloud, and our CMAQ scaling, it was showing that it has a strong scaling up to 192 CPUs. After that, we have a diminishing return, so we can use go from 64 to 128, 128 to 192, and you will have a good performance. And ARM architecture, we will like to support that because it has better performance over x86 64, and storage is always a major cost driver. So we suggest that you run for 2 months simulation and keep the last data or the secret files with you and move the data to the S3 bucket after post processing, and you procure a small S3 small luster storage, and so that you can save more with the luster storage, so you will save more money. And this process can be applicable to other HPC application other than CMAQ. So thank you for listening. I'm ready to take questions now.
That's great, Manish. Thank you. I see something coming up. Thank you, Kristen. Are there any questions from the community? You can type directly on the QA panel, or you may come off mute and then ask orally. Go ahead, Alex. Are you able to come off mute, Alex?
Here we go. Uh, thanks. Great presentation. I have a question about when you're saying you're moving stuff to S3, are you like using the CLI, the command line interface, or are you just directly um, like from Lustre, you have mounted S3 and just running stuff on the bucket, kind of. Does that make sense?
Yes. So yes, we are moving from Lustre to S3 bucket directly. We can use the S3 copy to use that. S3 copy command, we are using it to copy.
So because you could mount the bucket directly to Lustre as a
Mm-hmm.
folder, right? And so when you have a
Mm-hmm.
run, you redirect it there, and so your files go directly to S3. So there's, I guess the moving is happening in the background, but you're not actually moving them, right? Like it's just one.
Yes.
I don't know,
Yes.
maybe a semantics, but cool. Yeah, just wondering about that.
Thank you.
And Manish, we have a question in the Q&A. What's your plan for automating CMAQ workflows in the cloud?
We are currently working on it. So let's see if we got more funding. We will definitely try to invoke all these things what we have discussed for work, automating jobs, post processing, like combine an hour to day just after the simulation is completed, moving to S3 bucket and see. So we are working on it.
Another question that came in is if you can again explain how you saved 4 times the storage costs with higher throughput.
Yeah, sure. Okay. So initially, when we set up our Lustre drive, so the default option comes with 50 Mbps keep tabibyte, or you can say terabyte. So the cost was, if you see here, our initial uh, annual run takes around 3 TB, and it's around, okay, 3072 GB. If we use 50% compression, you are going to 1536 GB. Okay, and the thing is, Lustre, you can provision the Lustre for either 1.2 TB or chunks of 2.4 TB. So the 50 Mbps, it has a cost of around 0.60 per GB per month. Okay. So when you are procuring 2400 GB, the cost is around $1,500. But when we use a persistent drive, which has higher throughput, like 125 Mbps, or a scratch drive, which has 200 Mbps, you can get the price is much lower. That is 0.145 per GB. Even with a scratch, it is much lesser. Okay, so with scratch, you will have around what I think is 0.13. So the cost will be around $350 when you're using 125 Mbps. So that means you have a higher throughput persistent drive, and it is coming at a lower cost, and a lower throughput which is coming at a higher cost. So 1500 divided by 350, that is around 4x cheaper than what you're having. So you can save 4x cheaper cost.
And let's just provide additional context from the documentation on the chat.
Thank you. Any other questions?
Manish, there's one more from Bonyang. I'm not sure if you can read it.
Just
Can you see it?
transferring. Yes,
Yeah.
I can see. So A very good question. The thing is, we have a open data program. So from Lustre storage, we copy our data to open data program and uh, S3 bucket, and from there we copy it to our local server. But definitely, when you are copying from Lustre to S3 bucket, it will incur cost. Okay, and when you are copying from S3 bucket to local, it will also incur cost. So that is true. But since we have an open data program, it is not incurring any cost to us.
Liz has a follow-on comment to Bonyang. Other questions from the attendees? I know there was a lot of information. We will post both the slides and the recording from today's session on the CMAS webinar page. At some point, Serena will take care of it. So look out for the webinar link on the CMAS Center pages, and you will see both the slides and the video recording from today. I'll give it another minute or so to see if anyone has other questions. And while you're thinking of questions, like I said at the beginning of the hour, look out for those dates I mentioned in terms of the training, the conference, and then the one-on-one help sessions we have for the community. And the next one is coming on April 2nd. And then the next webinar is on AMET on the web on an EC2 instance, and that'll be on May 14th. And if anyone else has another exciting topic to present to the community, please let us know. We'll be happy to schedule you after May 14th in the next several months of the year. Okay, if there are no other questions, I think we'll wind up and give you back a little less than half an hour. And thank you, Manish, again. Very nice presentation, very helpful. And thank you, Liz, for all the responses as Manish was presenting.
Thank you.
Again, if you have other questions, feel free to engage with us through the CMAS Center forum. You all know where it is. Feel free to post your questions there or join us on the one-on-one help sessions. Thank you all and have a great rest of your day.